All right, how's it going, everybody? We are here at the beginning of week 13. This week, we're going to carry on with our chapter 11 discussion, and we're going to pick up this week talking about series. Last week, when we started section 11.1, we looked at sequences, which was an ordered list of numbers. This week, we're going to kind of graduate that onto series, sums of sequences, right? We're just going to add up all the numbers that are in that ordered list. We're going to want to answer a lot of really similar questions as we had when we talked about sequences. Does the series converge or diverge? If it converges, what does it converge to? If it diverges, in what way does it diverge? There's some pretty typical questions that we want to ask both about sequences and series here. And we'll ask those again today. What we're going to do today is I'm going to kind of do this in a much different order than the book walks through these things here. Change some words apparently. We're going to first compare four simple series and identify some obvious and non-obvious properties of these series. And when I say that these are simple, I don't know, that's not a word I should be using right here at all. Some of these are not simple. The first couple ones are simple. The second, the third, and the fourth ones are going to give us a little bit of a run around here and trying to identify some of their properties. So what we're going to do is we're going to start with the easy ones here, and we're going to work our way over to some that are a little bit tougher to understand. Get a flavor for what some of the proofs associated with some of these ideas of convergence and divergence look like. I really think that this is a good section to sort of set us up to start thinking the thoughts that we're going to need to think for the rest of this chapter here. We're also going to get a lot of like basic details that are just things that people just know about series. And we're going to look at a little bit of the details to how we know those things, but those facts are going to need to be facts that we use repeatedly throughout the remainder of this chapter here. So, kind of actually understanding the stuff we're talking about today is very much going to carry throughout the chapter, particularly, especially associated with, I guess, these last two sums right here, but most importantly, this final one here. Before we get started here, I do just want to point out I am going to use the shorthand associated with series in most of this lecture here today. Notice that all of these start at a lower bound of n equals 1 and go off to infinity. We're always talking about infinite series, just like we were always talking about infinite sequences. We will talk about finite subsequences today associated with these series, but these, by default, if it is never indicated what the bounds are associated with a sum, it is always implied to be 1 to infinity. So I'm not going to have that written, as you can already see right here. This to me does mean sum the value n as n goes from 1 to infinity right here. So we have implied bounds on these sums right here. So we're just going to start this by walking through these sort of in a sense from easiest to hardest to understand here. And let's take a look at the convergence divergence that we'll see if we can determine some information about these four sums here. And again, this will really give us a good like flavor as to what to expect as to how to think about these types of things for the future. So for our first series, the sum of the integers n for all the integers. This literally says add up all of the positive integers is what this sum is doing for us here. And what's kind of important in this one, well, I hope that you can kind of guess as to what's going to happen to the sum right here. I kind of want to define a couple things associated with each sequence that we should be considering, or each series that we should be considering. For every series, there's always going to be two related sequences that we want to consider. One is the sequence that's a direct correspondence with the series, meaning let's just literally look at what are each of the terms in this big old summation out here, right? When we do this sum from n equals 1 to infinity of n, that is equal to 1 plus 2 plus 3 plus 4 plus 5 plus 6. And so what we can see is that each of the terms in that giant sum are literally just the positive integers. So the sequence that is related to this series, I'm calling it a sub n as we call our general sequences here. And these are all the terms that we're going to end up adding in our series, right? This is a sequence. If you add up the terms in a sequence, you get the associated series here. So here, this is just my representation of what are the terms that we're adding. This is a sub n here. The other sequence that we are going to be interested in building here is called a partial sum sequence. The sequence s sub n is going to give us how much did you get when you added up the first n terms. So S sub 1 says, add the first term in the sequence up. What do you get? Well, the sequence starts at the number 1. So all we get is 1. S2 is the sum of just the first two terms. 1 plus 2, that'll give us 3. S3 is the sum of the first three terms. 1 plus 2 plus 3, that'll give us 6 out there. So whenever you see S, S is indicating a partial sum, where S sub n is the sum of the first n terms in the sequence. Right? So let me just say here, S sub n equals sum of first n terms. So it's always the case that S sub n is a finite sequence rather than an infinite sequence like we typically deal with, because there is always only ever going to be n terms in S sub n. It's the sum of the first n terms. We could build a sequence S sub n then, right? So my general formation of S sub n is the sum of the first n terms. In the case where our terms are the integers themselves, we're just summing the first n integers. What I can see that we're getting as a result here is S1 is 1, and I see that in my S sub n sequence. S2 was 3, and so therefore that's the second term in the sequence. So this says if you've added up the first two terms, this is the second term in the S sub n sequence. If you've added up the first two terms in the series, then you'll have a total of 3. If you add up the first three terms in the series, your total is 6. I can see that here. S sub 3 is equal to 6. So the third term in my S sub n sequence is 6. If you were to add on 4 to that, you get 10. If you add 5 to that, you get 15. So S sub n is sort of like our cumulative sum so far. It's how much stuff have you added up if you're at the nth term in the sequence so far. So what I think we can see here observationally is if you let n go off to infinity, remember that the sequence a sub n is literally the terms in our sequence, and here we're adding up the integers. So it seems like the size of each term is tending off towards infinity as n gets infinitely large. As we go out an infinite number of terms, the size of the terms are also approaching infinity that we're adding up. It seems like our partial sums are also tending off towards infinity, and in fact even faster, because notice here the fifth term isn't just 5, it's 15. So it seems like the S sub n sequence is always above the A sub n sequence, and so if the A sub n sequence diverged to infinity, it had better be the case that the S sub n sequence is also diverging to infinity. Hey, what's up, Finding J? And finally, I think it's pretty reasonable, therefore, for us to conclude that the sum that we are interested in has a divergent value there, or I should say it doesn't have a value. It diverges off to positive infinity here as well. All right. So I don't think I'm blowing anybody's minds here. I'm saying when you add up an infinite number of positive integers, that sum will diverge to infinity. And that makes sense. We're adding up an infinite number of objects that all have a sizable size, right? They all are bigger than 1 at least. And maybe I just said bigger than 1 because I'm thinking about our second example right here. Right? So these three things are sort of our conclusionary statements right here, and these are what we're going to want to compare across each of our examples. What happened to the individual terms? Where did they go? Here, the individual terms themselves went off to infinity, so adding up lots of them took our overall sum to infinity. All right, we're going to see those change over each of our examples here. Now let's compare this to the series, the sum of 1, right? So this says to me we're going to add up an infinite number of terms where each of the terms is the number 1, right? So each of the terms in our sequence here is 1 over and over and over and over again. We're just adding up the number 1 an infinite number of times. You should notice that what that means to us is that as n goes off to infinity, what happens to our sequence? Well, it actually converged now in this case. And we're actually getting 1. It converged to 1. Finding J, I already acknowledged you. This couldn't possibly be recording. Alternatively here, if we look at the partial sums, if you add up the first one term, you get 1. If you add up the first two terms, then we have added 1 plus 1 and got 2. The first three terms, 1 plus 1 plus 1 is 3. So our sequence of partial sums right here is getting bigger and bigger with every additional term that we make. And so it seems, hopefully pretty obvious to you, that as we let n go off to infinity, our partial sum sequence is going to diverge there, right? Where this sequence right here, if you go an infinite number of terms, is going to become infinitely large. And therefore, I hope it's pretty reasonable for you to agree with me right here without any formal statements that if we add up an infinite number of ones, we will diverge off to infinity there, right? So neither of these two cases that we're looking at are very exciting, but we want to get comfortable with this idea that we're going to look at both the sequence related to a series, that's the a sub n in braces, as well as the sequence of partial sums associated with the series. That's always our S sub n in braces right there. And those are always going to help us identify some of the relevant features associated with the sequence, help us make some conclusions about what we see. So let's go ahead and look at a more exciting example now. And what we immediately want to do is compare it to our previous examples. And so I'm looking at here our sum of 1 over 2 to the n. So as n gets bigger, we're going to keep on taking larger and larger powers of 2. Um, Yeah, Coffee Gopher, I totally agree with you. The sequence series thing is always super hard for me to keep straight. I guess the way that I remember the sequence series distinction is that when I say a sequence of events, those events are going to happen in the order that I prescribed. Order does not matter for addition, and series is where we do addition. Order does matter when you're making an ordered list, and so a sequence does help get me there on that one. But I remember spending years every time I'd hear somebody reference a sequence or series, I'd be like, crap, I got to go look up if they were talking about the list or if they were talking about the sum right there. But again, a sequence of events is an ordering of events that happens. It's an ordered list. Sums are not ordered, so we're not talking about the sum. We're just talking about the list when we talk about a sequence. So that's my stupid little trick that I use to kind of get over the hump on that one right there. So when we're looking at this sum, the sum of 1 over 2 to the n right here, kind of what I'm noticing comparing it to our three sums that we've seen so far now is that in the sum of n, every term in the sum was bigger than the term before that. Yeah, a series is a sum because they both start with s. That's exactly a true statement right there. Exactly. Yep. When we summed the 1, every term in the sum stayed the same size, but we still diverged off to infinity. In our newest example now, we're going to see that every term in the sum is getting smaller than the previous term, right? We're going to see 1 over 2, then 1 over 4, then 1 over 8, then 1 over 16. They're going to keep on getting smaller than the terms that had come before them so far. And so we're thinking that now, in this case, it was pretty obvious that these two guys were going to diverge off to infinity because the terms that were included in the sum either were getting bigger over time or were at least staying the same value over time. So we were adding up an infinite number of objects and getting a size of infinity. But in this case here, what I am noticing is that these terms that I'm adding up are going to be getting smaller and smaller and smaller over time. So maybe they get smaller enough over time that this actually will converge. It's not directly obvious to us here. It seems possible to me that maybe this sum converges. At least it's more plausible than the first two examples, certainly. So let's do what we've been doing and let's look at our a sub n and our s sub n sequences here. In our a sub n sequence, this is just adding what are the terms that we're adding up in this sum. And what we're going to do is when we start with n equals 1, we're going to get 1 over 2 to the 1, which is 1 half. And hopefully this is not a terribly surprising list to you down there. We're just seeing all of our powers of 2, starting with 2 to the 1 as our denominators, and a 1 in the numerator always right here. Right? So this one I can just state sort of directly on one line. However, when we're talking about our partial sums, I need to do a little bit of math in my head to kind of help me see what's going on here, right? So our first term in the partial sums sequence, oh gosh, partial sum sequence S sub n is 1 half because that's just the first term. If we add up the first two terms, 1 half plus 1 fourth, well, I can get a common denominator. I can think of this as 2 fourths plus 1 fourths, and that's going to give us 3 fourths. I can do a similar thing here. Since this went out to 1/8, I want to get a common denominator of 8 for everything here. So that's 4/8 plus 2/8 plus 1/8 gives us 7/8 here. The fourth term in our sequence, a half plus a fourth plus an eighth plus a 16th, well, I can get a common denominator of 16ths. That's 8/16, 4/16, 2/16, 1/16. That'll give us a total of 15/16. What I want to ask you is, can you see a pattern for the sequence? For example, could you tell me what S sub 17 is going to be? I feel like I can see a pattern here. And the pattern that I feel like I'm seeing is associated with that number n, for example, being 4, and our final denominator. And I see what the relationship is between our final denominator and our final numerator in all of these cases. They seem to be off by 1. So what I'm seeing here is just by visual inspection, and again, I've been yelling at you guys for the last two videos, evidence is not proof, inspection is not proof, right? I'm not proving this quite yet here, but I do think I can see by visual inspection what we've got going on here. It looks to me like S sub n, the denominator term of S sub n, is always going to be 2 to the n, right? 2 to the fourth is 16, 2 cubed is 8, 2 squared is 4, 2 to the 1 is 2. I can see that n-related pattern right there. And what I can also see is that in each of the numerator terms, it's always just 1 less than that. So it feels to me like that's what I'm getting for the nth term in the partial sum sequence. I'm just seeing this by visual inspection. I didn't really do any like direct math right here. I just said, man, I recognize 2, 4, 8, and 16. as related to powers of 2. And oh, what do you know? Those can exactly match up with the n subscript on S in each of the cases there. So now my question to you is, what's going to happen if we let n go to infinity for our partial sum sequence? Now remember, this partial sum sequence, S sub n, is really describing what sum do we have so far. If we take the limit as n goes to infinity of our partial sum sequence, it should tell us what sum do we have when we've added up an infinite number of terms. So this seems like this should be a direct correlation with the actual sum associated with this series that we're looking at here. I guess I could say the sum of this sequence, but that would probably just make some mathematicians mad out there. But in any event, if I let n go off to infinity, I can pretty easily see what's going to happen here. Minus 1 is not going to make a huge difference, right? When we're plugging in n to be massive, massive numbers out here, this numerator is approximately equal to the denominator. And if they're equal to each other, then that hopefully is a good suggestion to me that it seems like this should be converging to 1. All right? So what it seems like is happening to me is it feels to me like this infinite sum of 1 over 2 to the n is not diverging. Even though we're adding up an infinite number of numbers, it seems like we're getting a finite result of just 1. And I feel like I know that because I'm looking at my sequence of partial sums of what's our sums so far. And I let these so far tend off to infinity. And it seems like we're not breaking over this boundary of 1 right here. There's two different ways that we can kind of visualize this. Both of these are not traditional math ways of visualizing things, which I think is a very, very practical thing for us to do here. One way we can do this is visualize what's happening graphically here. And another way is by a game, which neither of these seem directly sensible. All right, so here's what I'm going to do. Yes, there we go. That's a perfectly good sentence right there. Yes, and that's what I think we should be doing, Coffee Gophers. I feel like there should be an award for the most words in a sentence that start with S that are technically true surrounding Chapter 11 content. A subseries sees a sequence's sum split into sections. And especially they are starting sections, not just any old sections. We can have subsequences that are from any number of terms out there. Our partial sums will always be the starting sums out there, so we can get an extra S word in there right there. And so here's the way that I'm going to picture this guy. What I would like to do is sort of indicate where are we at so far with this guy. And so here's 0 and here's 1. Notice that if we are at n equals 1, then we have so far accumulated a length of 1/2 in total, right? But what we don't have is any of these other parts. Now when I go on to n equals 2, what I'm going to do is I'm going to keep my original stuff, right? We've still got 1/2 as the sum so far, but now what I'm adding on is a quarter. And what you should notice that 1/4 is 1/4 is 1/2 of a half. So what I know is that that is going to satisfy the rest, or half of the remaining distance left to go to get to 1. So this is 1/2 plus 1/4. Now when we get to n equals 3, we're going to keep the 1/2. We're going to keep the 1/4. And I'm noticing that what 1/8 is 1/8 is half of the remaining. There's 1/4 that's missing out here, and 1/8 is half of it. So it looks like what we're going to do is go half the rest of the way to 1. And so I think, I'm not going to draw any more lines in this right here. I think we can see what's happening. Every time we include the next term, in our series, which is our sum, it takes us half the rest of the way to 1. I know that's a weird way to phrase that right there, but all I'm saying is every additional term closes half of the gap between the sum that we have so far and the number 1. So a thing that I like to explain, and this is, I'm just picturing now back to like teaching college algebra, right? This is me saying things now like, so if every time we include a new term, it takes us half of the rest of the way to 1, then what I know is that no term will ever take us all the way to 1, right? This is telling me, this is a guarantee for me that we are bounded above by 1. Further, since we can also see that S sub n is monotonic increasing, we can conclude by the monotonic bounded theorem that that S sub n converges, right? Now remember, our monotonic bounded theorem from last class was about sequences converging. But what I feel like we're seeing here is that if a sequence of partial sums converges, that is equivalent to the sum itself converging, because the partial sums is what we've added up to so far. And if what we've added up to so far as n goes off to infinity does converge, then the sum itself has converged to that value right there. Now, remember, the last caveat to the bounded monotonic theorem, or whatever it was called out there, is all it tells us is that we do converge. It doesn't tell us what we converge to. According to the bounded monotonic theorem, it still seems possible that this series actually converges to 0.99 and not 1, because I've never seen a value bigger than 0.99. All I know is that it does converge to something 1 or maybe less. Not 100% clear here, right? So what I'm going to now show you is an alternate way to think about this guy. This is a bit more of a ridiculous, I certainly don't want to call this proof right here, but this is like a way that I've come up with thinking about this is as a probability statement, right? I'm going to use a probability statement here to justify the convergence of an infinite series. Right? So here's my, and this is kind of ridiculous, but again, I want us to like open our minds to thinking about these things rather than just being like a series is a sum of numbers. I think that that's a super narrow-minded way for us to view this. It's going to limit you in the comparisons that you can make to other scenarios here. So here's my game for you. We're going to play a game where you flip a coin until you get a heads, at which point you win. All right. To win this game, you are just going to flip a heads. All right. What I want to know is what is the probability that you eventually win? All right. Now, this just says flip till you get a heads, right? So even if you have the worst coin on in the universe, the most unlucky coin that's ever been minted by man or by anybody else for that matter, it seems like you're eventually going to win, right? With an infinite number of tosses of a coin, I hope that we all agree, especially if this is a fair coin, as I'm intending this to be. If you have a fair coin, then over an infinite number of tosses, we absolutely expect to see at least one heads, at least one tails, right? So if we just keep flipping this coin, probability of an eventual win. So I think I'll say here the probability of an eventual win is 1. There's a 100% chance that if you just sat and flipped a coin for the rest of your life, that you will eventually get a heads, and that will make you a winner in this game. Right? Now, what I want to ask is how could this happen? Win on the first flip, or win on the second flip, or, and I'll just put the dot, dot, dot right away because I think you can see the pattern that I'm setting up here. We could just say you're either going to win on the first flip or on the second flip or on the third flip or on the fourth flip or on the fifth flip or on the sixth flip, and we could just go forever and just say add up all those probabilities. That's the probability of you eventually being successful here. Well, I can do this sum right here, right? I know that my probability of an eventual win is 1, and I know that my probability of an eventual 1, well, let me kind of rewrite this a little bit better here. This is the probability of, let me write this, win on first, plus the probability that we win on second, plus the probability that we win on the third. That's what we're claiming is the probability of an eventual win, which is 1. Right? Now, what is the probability that we win on our first flip? What do we need to get in that case right there? Well, if we win on the first flip, then this was just getting a heads. If we won on the second flip, then I know that that means that I got a tails on the first flip because I didn't win on the first, but then I did win on the second. So that's going to be tails heads. This one, we would have had to have gotten tails twice and then a heads third if we did win on the third. And we could just keep on adding up these things. Or we got tails 3 times in a row before we got heads. Or we got tails 4 times in a row before we got heads. Well, we can compute all these probabilities. What's the probability you flip a coin and get heads? That's a 1/2 probability. What's the probability that you flip a coin and get 1 tails? That's a 1/2. And then get a heads? That's also a half. What's the probability that you get 2 tails? Well, that's 1/2 squared. And then a heads? That's also a half. So here we're going to get 3 tails. So that would be 1/2 cubed. And then 1/2 for the heads. And so notice, what are we adding up here? This is 1/2 plus 1/2 squared plus 1/2 cubed plus 1/2 to the fourth. And we have to go infinitely far out there, right? Technically speaking, there could be somebody that makes it a billion flips of tails in a row before they get their heads. We have to accommodate for all possible probabilities out there, but it does seem like we're saying here. So I kind of like this as a game suggestion that shows us the convergence of an infinite sum right there, which is a very strange way to go about thinking of things that are like this. It turns out there are some people that have put together tons of just like super freaking cool proofs that are like this one, where they use kind of really roundabout ways to prove sequences in series convergence or divergence. And I've even seen, I wouldn't go so far as to say that this is like a book, but it's sort of, I guess it's printed as if it's a book, and it's got like 20 or 30 different proofs that are all where they have built a game to prove some idea. So like this one right here, I came up with a game where it turns out that the probabilities associated with the outcomes of the game are exactly equal to a sum that we want to know. And we have intuition that tells us, since we know that we'll eventually win the game, there's a 100% chance of winning the game. That's the number 1 that we're looking for here. And so it kind of helps us put together the pieces for us. And so I've seen a book that like literally constructs board games, and they say, by playing this game, you will see that the sum of blah 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 is equal to blank, and it's like, oh my gosh, holy crap! How did you figure out to show this as a representation like this? There's lots of really like interesting ways that people kind of show some stuff that looks like this out here. So I like this just in how different this is from the ideas that we're thinking about right now, is like lists of numbers, and this is a coin flipping game, but it still tells us the same types of things that we're interested in knowing here. So here's what I'm seeing. It seems like, here's some important things. It seems like if we let n go off to infinity, what happens to the nth term in our sequence? Well, since the nth term in our sequence is 1/2 to the n, as n goes off to infinity, we're getting like 1 divided by infinity. Our numbers are going to get infinitely small, down to 0. Another thing that we saw here is it seems like if we added up our partial sums, it seemed like they were getting closer and closer and closer to 1. And I saw this because I was able, in this case, to actually come up with an expression for this, right? In this case, we were literally able to say what the expression for s sub n was, that this was going to be limit as n goes to infinity of 2 to the n minus 1 over 2 to the n is equal to 1. That's our equivalent statement that goes with that. And ultimately, it seems like what we want to conclude then, therefore, is that that sum is equal to 1. Just like our limit of the partial subs, our limit of the sequence of the partial sums was equal to 1, so must our sum itself be. It seems like these are super closely related, and the reason that we get both of them is because people often feel uncomfortable about this idea of saying, what does it mean to add up an infinite number of objects? If we can instead reinterpret our sum of an infinite number of objects as the limit of a sequence of partial sums, then maybe we can now just use our old convergence ideas about sequences to help define our convergence ideas about series right here, since we can re-express one in terms of the other, right? So that's why this S sub n, our sequence of partial sums, is very valuable, because in a sense what it's doing is it's re-expressing a series as a sequence. And therefore, we only need one set of rules to help define our convergence and our divergence. So we've done 3 of our example series here. And every time you hear me say it slow, it's because I'm like, wait, sequence series, because I can't keep it straight either. And our last basic example. What I want to say is 1, this is not a basic example. And 2, don't just think that this is some like trivial base case right here. This is by far the most important series for you to know. Knowing about the series, the sum of the 1 over n terms, is the most important series that you will learn about in this chapter. It is the one that we will most often compare against when we are looking for divergence, convergence for other more difficult to handle series and sequences out there. All right. So this is saying we're going to add up an infinite number of terms where the nth term is 1 over n. Right? So let's still start out this exact same way. Let's start by looking at our 2 related sequences that are associated with this series. The first sequence is just what are the terms in this sum. When n is 1, we get 1 over 1, which is 1. And for all the rest of them, you can see that we're just getting 1 over n for the nth term out there. The 6th term in our sequence is 1 over 6. We're going to add all these guys up, and we're going to get our series right here. All right. So we're looking at our partial sums here, and what we're seeing is not quite the same action as we saw in our previous example, right? I'm adding 1, 1 plus a half, 1 plus a half plus a third, 1 plus a half plus a third plus a fourth, and 2 things are happening to me here. Oh, I should stick to my patterning right here. So 2 things are happening here that are different than what we saw before. 1, every time we get up to a point where I'm thinking to myself, well, maybe this is going to stop at the next integer value. It didn't seem to do that, right? We walked right over 1 to get started. And so I said, okay, maybe it limits itself at 2. Walked right over 2 only by the 4th term right there. So it seems like these partial sums are getting bigger. But I also can see that what's happening to my 1 over n term is that it seems like it is getting smaller and smaller. I can see that the individual contribution that's being made by the nth term is getting infinitely small as n gets infinitely big. So it does seem to me like the contribution from the nth term is tending towards being 0 as we get off into those massive terms out there, right? 1 over a trillion is going to be the trillionth term in our sum here. How much is that really contributing to our overall value? Are we really going to diverge off to infinity here? It's not super clear. So what I'm seeing is that I don't have any at least guess for like a bound I could place on this, right? It obviously gets over the 1. It obviously got over 2. It's not obvious to me that it's going to get over 3. I'm not sure about that. But we've only checked out the first 4 terms. So I'm going to say, let's go ahead and write a little bit of Python for this. Just one little line of code. I just need a calculator to help me add up a bunch of terms right here. And I don't want this to be hard. It's going to be a little easier for me to write some code. All right, Coffee Gopher, let's see what you got here. A subseries sees a sequence's sum split into sections. Ooh, now we're getting somewhere with that. Now if we could just get like an A-B rhyming scheme with that and get some lyrics going on, now I think we're getting somewhere. Very good. All right. So let's pop over into Python here and let's see a little bit of code that we can write to add some of these up for us. All right. So what I want to do is I want to write a function for myself that's going to add up the first n terms in our sequence. So I'm going to define a function that I'm just going to call s sub n. Make this a little bit bigger so that we can all see this here. My function is going to be called s sub n. What information do I want to give it? Well, I need to tell it which n are you referring to so that it can tell me, oh, you wanted s sub 7? Here's the sum that we've got so far, our partial sum calculator. So what I want to do is I want to return to myself the sum of a list of numbers. All right, and maybe let me do it like this just so I can be reasonable. What's the sequence that we're building here? Well, it's a list, so I'm going to put it in brackets, and it's going to look like 1 over x. For which x's? For x in range. Where do we want x to start? At 1. And we want to go up to the nth term. Just remember the one slightly dumb thing here in Python is that the lower bound is included, so it would start at the first term. But if I just did n right there, it would go up to, but not including the nth term. So as it stands right now, this would only give me the subsequence up to n minus 1. So I'm going to buffer give it an extra one right there. So when it goes up to, but not including n plus 1, now it'll just give us up to the nth term right there. So that actually fixed our deal right there. And in fact, just to verify this, let me just do this right here. And let me do, So when you do this now, I'm not actually done here. I'm just kind of double checking my work. This is only giving me the sequence, the first n terms of a sequence. Um, yeah, I know, Coffee Gopher. You're telling me, man, 20 years from now, all I'm going to do is just be in Python for the entire lecture, and everybody's going to be down. It's going to be so much easier. But I can see I'm getting 1 as my first term, 1 over 2, 1 over 3, 1 over 4. So it does look like I got the first 4 terms. So what I really want is I don't want the sequence itself. I want the sum of the sequence. So now when I update this, this should now be giving me my 4th subsequence. And this is exactly what we saw when we were back over here in Word. I had that exact value sitting right there. We can see it 2.08333. And when I'm back over here, here's my 2.08333 when we sum up the first 4 terms. So obviously what we came to Python to do is not to have Python add 4 numbers for us. If that's what you're using computer programming for, then we'd never need to be computer programmers. I want to know what happens when this number gets huge, right? So maybe let's check out like 100,000. This will say, add up the first 100,000 terms. I want to know what's S sub 100,000 here, and I'm getting 12.09. So, I don't know. Does this mean to you that you think it's converging or you think it's diverging right here? On the one hand, 12 is not a very big number. On the other hand, it seems like it keeps on like crossing over like some integer thresholds that I might expect it to stop at, and it's not. I mean, all right, let's go ahead and do some more here. S sub n of, so there's 100. There's 100,000. Let's do 100 million. What's the sum of the first 100 million terms in this series here? This one's going to take a little minute. Uh, Even our computer and even my fast computer here is probably going to take a hot minute to add up 100 million numbers right there. But okay, so we just added up the first 100 million terms and we got almost exactly 19 right there. I feel like this number just keeps on getting actually like meaningfully bigger, right? It doesn't seem like it's converging to anything to me here, but it's really hard for me to make this judgment call. So let's at least kind of go record what we've seen so far here. What I just saw in my Python code was that we looked at the sum of the first 100 million terms, and we got, what did I just get right there? 18.99789. I'm going to change this to 18.99. I'm going to not do some rounding right there. That's incorrect rounding, but whatever. We're in the ballpark of where we're looking at. I feel like this just keeps getting bigger, but I can't really tell what's going on right here. I honestly feel like this is not great evidence for convergence or divergence right here. What you got to remember is that beyond this point, every number that we're adding into this sequence is, or adding onto this series, is smaller than 1 divided by 100 millionth. They're all smaller than 1/100 millionth. Are we really diverging off to infinity with all the remaining terms that are all out there? We've only added up to 19 in the first 100 million terms of this sum. But since I don't see this ever like slowing down, it seems like every computation I've done has given me like a meaningfully larger number than the previous computation. I'm getting suspicious that this sum maybe diverges. And what I want to look at now is 2 different ways that we can show that this sum diverges. I want to suggest to you guys that I don't think that there is any reasonable way that you guys should be expected to necessarily come up with some of these proofs on your own. Um, but I do think that you can absolutely, and in fact, you need to understand my logic in how these proofs work. I'm going to put the word proof in air quotes right there because these are not the most rigorous proofs ever. There are some details where we're saying, and we can see that that's happening, right? Instead of proving it, we're just sort of saying it. So these are not proofs per se. If you go to grad school, these will not be counting as full credit for your homework, but these are very sound logical arguments that we are making here. And the logic that we're using is logic that you are going to be expected to use in the upcoming sections that we're seeing here. So really make sure that you stop and see like what is the big idea behind this thing right here. All right. So I'm going to do this 2 different ways. I'm going to do this the way the book shows, and then I'm going to do it the way that I remember learning this myself. which is a little bit different way. Both of these are going to use a technique of grouping. Oh man, Coffee Gopher, you're going to love this one now. A grouping technique of taking groups of subsequences of numbers within our series or sub-series within our series and showing that they're all of at least a certain size or they're bounded by some certain size right there. So first I'm going to show you what the book does to show the divergence of this sum. Then I'm going to show you one that I've seen right here. So doing C, I agree with you, Coffee Gopher, that C will probably have performed that computation slightly faster than Python performed that computation. But I also think that the average person could write that Python code faster than they could write the C code. And so the typical trade-off there is that if you are doing like we just did hundreds of millions of calculations, it is more useful to do a lower level programming language like C, like Java, or even, and don't ever learn Fortran if you don't have to, but like Fortran, because it will be able to do those computations more efficiently. The reason people like Python is because they can just blurt some code out on screen and it just works the first time, as opposed to like having to do like some real coding, which is what you'd probably have to do in most of those other settings. So Python's trade-off is always its writability, even though it runs slightly slower. A typical case then is that if any company finds out that if a company needs to compute some sum of 100 million terms for every customer that comes in the door, then what they will do is they will prototype their code in Python because it's easy to write. Once they know that it works, they will then write that piece of code in C. Even though it might take a little bit of work to write that code in C, it'll run faster for the large number of uses that it's experiencing right there. But I generally think that unless your goal is to become a software engineer, I don't think that learning languages like C is necessarily beneficial for a first language that a person should learn. But if you're going to become like an engineer of some kind that's going to care about speed of computation, then certainly learning those lower level languages is very, very practical. I like blurting stuff out onto pages, and I'm rarely computing things that take an intense amount of computation like billions or trillions of computations. And so I have pretty limited uses of when I need to go into those lower languages right there. Um, yeah. Well, and again, Coffee Gopher, with your majors that you're talking about right there, I mean, I kind of like to tell everybody that I think the most practical minor that you could ever get is math, or computer science, because you need to be numerically competent. You need to be able to compute some things, whether it's you doing the computation or a computer computing some things. I think that those are, regardless of what your major is, I think that the two most practical minors that exist in the United States are math and computer science, and because both of them kind of for that same reason right there. So, so here is our first soft proof. And again, we're skipping over some details, but I think that the argument is well made right here that everybody can sort of agree with what we're going to end up seeing here. So what we're going to do is we're going to list out, oh, by the way, let me back up real quick here. I think I skipped over saying something important. This sum right here, our 1 over n sum, again, it's a super important sum. We're going to compare a ton of things against it, and it has a name. And so you're going to see this name a whole bunch this chapter. The harmonic series is the sum of the 1 over n terms from 1 to infinity. It's a very, very, very important one for sort of our measurement. Which things are bigger than it, which things are smaller than it is the super common comparison that we want to make. So you're going to see reference to the harmonic series a bunch more this chapter. And so, and by the way, this thing is typically denoted just capital H. Capital H is our value for the harmonic series, or H sub n would be our subsequence right there, our sub series right there, our partial sum. And so H should be our 1 plus 1/2 plus 1/3 plus. And I'm going to have to write out a bunch of these so that we can see a pattern here, because we're going to group some stuff together. And this is going to be true for both of our techniques for showing this stuff here. All right, so here's our first 11 terms in the harmonic series, and it goes on forever. All right. What I'm going to do is I'm going to imagine for myself some related terms that are associated with these. So I'm going to stack these guys vertically with some terms that I want to compare them to. And what I'm going to say here is that G, I'm going to make a new series, all right? Its name is G. And the important thing that I'm going to do right here is rather than writing 1/3, I'm going to use a slightly smaller number in its spot for right now, 1/4. And I'm going to leave this 1/4 alone. Then I'm going to take my next grouping of terms right here, all right? And just like here, I changed my denominator of 3 to my next highest power of 2 of 4. I'm going to take, and notice here, by the way, these groupings of terms, by the way, that looks to me like it's a 1/2. I'm going to do the same thing right here, and I'm going to group together. I'm going to need 4 of these terms. I'm going to call this 1/8 plus 1/8 plus 1/8 plus, and then leave this one alone. That's actually 1/8. And you should notice that if you add up 4 copies of 1/8, that's 4/8. Well, that's also 1/2. And so what we're going to keep on seeing here is that we're going to be able to keep on grouping up these terms. That'll be a 1/16 plus 1/16 plus, and we're going to add up 8 copies of 1/16, and we're going to get a 1/2 again. So it looks to me, I can make 2 conclusionary statements here. The series G is smaller than H. That's statement number 1 that I want to make. The way I can tell that G is guaranteed to be a smaller sum overall than H is because every time I replaced a term, I replaced a term with something smaller than it, right? 1/3 was replaced with 1/4. 1/4 is smaller. 1/5 got replaced by the smaller number 1/8. 1/6 smaller is 1/8. 1/7 smaller is 1/8. So every time I replaced a harmonic series term, I replaced it with something smaller than what was in the harmonic series. Therefore, our total series G should be smaller in size than H. All right? What I can also see here is G is equal to 1 plus 1/2 plus 1/2 plus 1/2 plus, and how many 1/2s? Well, an infinite number of them, right? So this is really equal to 1 plus the sum from I equals, or I should just call that n equals 1 to infinity of 1/2. We're adding up an infinite number of 1/2s as long as we group the terms in H appropriately. This is going to diverge to infinity, clearly, since we're just literally adding the number 1/2 an infinite number of times. And so finally, I think that we can conclude. So let's say since G diverges to infinity, and H is greater than G, H must also diverge. All right. So a sneaky little grouping that we just did right here. Now notice something that I think should kind of bother you, and I think I should be able to easily convince you that it's not really an issue here. Clearly what we're doing is we're taking larger and larger groupings of terms, right? It was 2 1/4 made a half. It was 4 1/8 made a half. It was 8 1/16 that made a half right there. So every grouping that we do, we need twice as many terms to accumulate it, right? But how many terms are in an infinite series is an infinite number of them. So I don't care if eventually you're grouping these things trillions at a time. We're never going to run out of terms. There's always going to be another group twice as big that's going to follow after it that you can again add up to get to 1/2 once again. So it is true that the series G, in a sense, sort of has like a log base 2 number of terms, as many as H has. But the log base 2 of infinity is still going to be infinity, so it still has an infinite number of terms. Maybe this is just like my dumb little statement right here. Log base 2 of infinity equals infinity. This is number of terms in G and number of terms in H, right? If H has an infinite number of terms, then it looks like we're going to be grouping these up by powers of 2 numbers of groupings right there. So it should have something on the order of, so I should at least say on the order of log base 2. But I don't care. If you're going to plug in infinity into log base 2, you're still getting an infinite number of terms. So we're still adding up the number 1/2 an infinite number of times. And the infinite sum of 1/2 is infinity. And so again, G we know is smaller than H because every replacement was with a smaller number. But G clearly diverged to infinity. And if G is diverging to infinity and it's smaller than H, then H definitely diverged to infinity because it's even bigger than that. So that's cool, right? So again, I don't ever expect you guys to be able to come up with this proof on your own, but I certainly expect that you can see what adjustments that I made to come up with a new series, and I think that you can easily see the arguments that are being made right here. we've added up an infinite number of 2's, and we know that our series that we've made is smaller than the series of interest. So I'm going to, before I walk away from this one, I want you guys to really realize what's happening here. We made a direct comparison between 2 series. H, we didn't know about. G, we did know about. Since we knew about G, we were able to make a meaningful comparison between G and H that allowed us to conclude exactly what we wanted to conclude about H. Making comparisons is a huge, huge deal when we're talking about sequences and series. Since so many sequences and series, we can never specifically pin down the individual sequence or series, but we can say what its relationship is to some sequence or series that we can pin down, and that often allows us to still draw the conclusions that we're interested in drawing right here. So this comparison idea is a really important idea, and so playing some of these grouping games is a very important thing to be able to do. So I want to show you a second strategy, and this is the one that I remember when people say to me, you know, when I get asked at a bar at midnight, hey man, can you prove the harmonic series diverges? And I'm like, crap, I think I can. Give me a napkin and a pen. This is the one that I actually write down late at night when I'm reaching for a harmonic series divergence proof right here. And this is going to be a proof by contradiction. All right, so proof by contradiction says assume something that we don't think is true, use it and let it take us to a crazy place so that we can conclude that that original assumption must have been false. So what I'm going to do is I'm going to say assume that the sum from n equals 1 to infinity of 1 over n converges to a value h. Right? We don't actually think this is true. We're trying to show that it diverges. I'm going to assume that it converges and let this take me to an unreasonable statement, which will say that I must have had an incorrect hypothesis, that I must have assumed the wrong thing up there. Yeah, you know, Coffee Gopher, I've proven some crazier things in those situations. I tell you what. That's why I got to come up with the best case one I can remember. I can't just come up with my whole list of divergent proofs out there. So here's what I'm going to do. I'm going to again start with my sum for h right here. It's 1 plus a half plus a third plus a fourth plus a fifth plus 1/6 plus 1/7 plus 1/8, blah, blah, blah. And it looks like we're doing kind of a similar thing that we did right here. So what I'm going to do is I'm going to again make a comparison right here, right? What I want to say is that our harmonic series, I'm not going to like rename this something like G, but we're kind of doing a similar thing right here. What I'm going to do is I am going to swap out some terms. And in fact, what I kind of should do right now is I'm not going to make the claim before I swap out the terms. I'm going to swap out the terms and then make the claim here. So what I'm going to do is I'm going to do this swapping right here. Wait a minute. What's my? Oh yeah. Sorry. Oh, that's not. Oh yeah. Okay. I see what I'm doing stupid here. Okay. So what I'm going to do in this one is a similar move to what we did before. I'm going to get myself a 1/4 and a 1/4 there. So you should notice 1/4 is smaller than 1/3. Over here, I'm going to do a similar thing. Instead of 1/5, I'm going to use a smaller number, 1/6, and keep that partnered up with the 1/6. I'm going to swap out 1/7 for a number that's smaller than it, 1/8. Right? And what we're going to see here is that this, now I got to come back. I accidentally wrote an equal sign right here. I didn't mean that. What we have clearly come up with is the fact that our harmonic series above that we're claiming converges to h, that h number needs to actually be bigger than this sum. This stuff is smaller because I've swapped out some terms like 1/3 for its smaller partner 1/4, 1/5 for its smaller partner 1/6, 1/7 for its smaller partner 1/8. So this new sum with the parentheses in it is smaller than our old sum h. And what is this thing that we're looking at here? It looks to me like this is 1 plus 1/2. What do you get when you add a fourth and a fourth? That's 2/4. That's 1/2. What do you get when you add a sixth and a sixth? That's 2/6. That's 1/3. What do you get when you add an eighth and an eighth? That's 2/8. That's 1/4. Well, do you recognize these terms that we're kind of building up right here? It looks to me like with this being the odd one out, all the remaining terms are giving me, so it really looks like, I'm going to draw this guy up front right here. This is 1/2 plus 1 plus a half. Oops. Okay, good. 1 plus a half plus a third plus a fourth plus all the way out there. And so it looks like we're now making the claim, dragging this h on down here, that h is greater than 1/2 plus h. There's no way that can be true, right? H is clearly a positive number. There's no way that we're going to add a half to a number and get something that's smaller than the original. Uh, I guess my word for this is contradiction. Is a proof by contradiction. So what we did is we assumed something that we thought was wrong, and we let it take us to a crazy place. Here's our crazy place where we're saying a number is bigger than that number plus 1/2. That's literally not true for any number that there is, right? So by assuming that this did converge to h, we were able to lead that ourselves to a crazy place. And since we're in a crazy place where that can't be true, it must be the case that our assumption was wrong. Right? And, oh, don't go with me wrong. And since it does not converge, it diverges. Right? So a proof by contradiction, you assume something that you think is the opposite of the truth. You let that take you to a very clearly wrong place, right? It's not clear that this statement is wrong. It converges to H. That's the thing that we don't know about. That's the unclear statement. But we assumed that this was true, and we let this take us to a place where we knew that we had a false statement. Since every statement between this line and this line is an equivalent statement, it must be the case that all of these lines were wrong, including this last one, that this sum converges to h. And since that's wrong, the only thing we could say otherwise is that h diverges rather than converges for this sum that we've got right there. Right? So these are kind of two different ways to show the divergence of the harmonic series. Both of them involved us doing some very smart selection of some subgroupings that are going on out here, right? And again, notice that sort of in a sense, if this sequence, both of these series do have an infinite number of terms, but the second series, in a sense, collapsed two terms into one term in almost all cases. So in a sense, on the second line, it's sort of like there's half as many terms, but half as many terms as an infinite number of terms is still an infinite number of terms. And so we do not have any issues with the dots out there. We had an infinite number of terms. We grouped them all pairwise except for the first two, and we got a new infinite list of terms where every term from the original sequence or series was included, with a bonus 1/2 also being in there, despite the fact that we made it smaller when we made that change. There was more quantity in there, so it must have been wrong. Therefore, our original assumption was wrong. Therefore, H diverged out there. So again, these grouping strategies, very useful strategies. And again, I can't emphasize this one enough. It's like our biggest overarching theme maybe of the whole chapter is we don't know what to say about most sequences and series. So the few cases that we really do know what's going on, like this, now we know that the series 1 over n diverges to infinity, we can use that as a comparison case to compare against our things that we don't understand and help us say, oh, well, since the harmonic diverges, and this one that we're looking at is larger than the harmonic, this larger one must also diverge off to infinity. Even though we can't make any direct statements about it, we can make indirect conclusions by these comparisons. This is one of our most important comparison series that there is, the harmonic. So even if this series itself isn't the practical one, it's the one that we use to compare against for like all other series that are out there. It's very, very practical. It's a comparison-based series here. Cool. All right. So let's talk about some theorems here, and then we'll do our last bit of computation and call it a day. Cool. We're right at an hour here. So these first three statements are things that we've sort of just seen. The last one is one that's going to require us to do a little bit of math here. Well, more math than we've honestly done so far today. So some theorems about series. And by the way, these are all four listed in section 11.2, but I think that I have all four of these in a different order because I talked about some of these topics in a little bit different order here. So statement number one, given some series, the sum of a sub n terms, we denote the nth partial series as s sub n. That's notice here, we're only going up to the nth term now. It's the s sub n, the partial sum up to the first n terms. Oh, and I guess the way that I wrote this should be e sub I, whatever. I'm technically keeping my subscripts appropriate right there. And so if the sequence of the partial sums converges to some number s, then the series itself also converges to that number s. So what this is saying to us is just that it's a bit hokey to say that you know what you're going to get when you add together an infinite number of numbers. Therefore, we instead consider the sequence, the associated sequence of partial sums, and we can talk about its convergence or divergence a little bit more clearly. Right? So we're just saying there's always this relationship between an infinite series and the sequence of partial sums. And if we can ever prove that the sequence of partial sums converges as a sequence, then that's going to tell us that the series converges as a series and both to the same value. Right? That's really important. So this theorem right here is our direct link between convergence of a series and convergence of a sequence. Right? So this is what gives value to us being able to compute the partial sum sub-series or subsequences associated with the series. Our next theorem about series here says, if a series, the sum of a sub n, is convergent, if it does converge, it must be the case that the individual terms a sub n go down to zero. And a good thing for you to think is, otherwise, if it weren't the case, then we'd have the limit as n goes to infinity of a sub n being not zero. Then that means that there's still some size associated with every single term that's in the sum out there, right? If the limit as n goes to infinity of a sub n was 0.1, then what that tells me is that we're adding up an infinite number of terms that are probably all at least as big as 0.1, and an infinite number of 0.1s would diverge. So it needs to be the case that our eventual contribution to this sum goes down to zero, that the very late terms in our sum are contributing essentially nothing, and that it was that most of our contribution was from the earlier sums. Very importantly, notice that the converse is not true. You should notice that when we looked at our harmonic series here, 1 over n, it was the case that as n goes off to infinity, the individual terms do get infinitely small here, but it was not the case that we converged, right? So we cannot turn this statement around. A implies B is true here. It is not the case that B implies A going backwards out there, all right? So we can't flip this guy around. The converse is not true. The harmonic series is our counterexample of the converse. In harmonic, limit as n goes to infinity of 1 over n equals 0, but the sum of 1 over n is divergent, right? So that's our counterexample for the converse. This guy has sort of a partner statement about divergence right here. It says, if the limit as n goes to infinity of the individual terms of the series, the a sub n's, doesn't exist, or if the individual terms don't converge down onto zero, it must be the case that our sum is going to diverge, because that means we're still going to be getting a non-trivial contribution even from those late terms that are out there in the series. So again, this means that we're adding up an infinite number of terms that have like non-zero accumulation associated with each one of them. And so we will get something of infinite size out there. It is going to end up diverging, right? So 2 and 3 are sort of partner statements. Number 1 was just sort of relating our convergence of the partial sum sequences is equal to the convergence of the series itself right there. Number 4 is our final thing for the day, our final idea for the day, but it's going to take us a little bit of work and a couple examples we're going to want to see, but these at least aren't proofs, which I know that everybody is probably less excited for than computation. And the final thing is to say here, there is a known formula for what sum you will get, for what your convergence value will be for infinite sums if what we're adding up is what we refer to as geometric terms, if the series is a geometric series. A geometric series is a series where each pair of terms has the same common ratio. So notice here, our common ratio, I can look at successive terms, right? AR over A is the same as AR squared over AR, is the same as AR cubed over AR squared, is just R, right? So R represents the common ratio between terms. If you divide one term by its previous term, R is what you multiplied by to get from one to the next. So this is really the representation of like an exponential function, right? We're doing the same multiplication each step of the time, starting at the value of A. Also notice that at the first term in the sequence, I've got eyes down here again. At the first term in the sequence, when you're plugging in n equals 1, n equals 1, the reason why there is an AR to the n minus 1 instead of just AR to the n is that when we do plug in 1 as the first term, we'll get 0 as the power. R to the 0 is going to be 1, and we'll be left with A as just the first value that we're going to end up seeing in that series right there, or the sequence. A geometric sequence is an acceptable thing to discuss as well. So what we want to try to do here is let's try to find what do we get when we, like what's a pattern for S sub n in this case? It's not really clear. We want to identify, can we see a closed form equation for S sub n? What we know is that if this is going to converge, then the convergence of this sequence would be the same as the convergence of this series right here. So if I want to know what this series converges to, that's equivalent to me finding its sequence representation for the partial sums and taking the limit as n goes to infinity and seeing what our partial sum eventually becomes, right? So here's the way that we're going to do this. This is on the long, long list of things where I don't expect that you would ever come up with this on your own, but as soon as you see me do it, you should say, yeah, that makes sense, the algebra that he just did right there. So what I'm going to do is this. My goal is to solve for S sub n, but I need it to not be in some crappy form like this where I can't do the computation, right? This isn't really a helpful format for me right here. If I have to do n computations to solve for S sub n, then it immediately is becoming not very practical for me, right? So S sub n, by definition, is just this, I'm just literally copying down from immediately above right here. Very importantly, the one thing I'm not copying down from above is that this is an infinite sum, so there's an infinite number of terms, and it stops at the dot, dot, dot. This is a partial sum of the first n terms, and so it stopped at n minus 1. We plugged in n in for n and got the n minus 1. There are n total terms out here from n equals 0 up to n equals n minus 1, right? From 0 to n minus 1 is a total of n terms. Now, what I would like to do is I would like to not have n terms out here. So a good thing to always think to ourselves is if I could somehow cancel away a crap load of these, that would help me out a whole lot. And the way that I can kind of see that I can do that is since all of these terms differ from their neighbor by only a multiple of r, it makes me wonder, what would happen if I multiplied our original S sub n sequence by r? Well, I can see that my first term, instead of just being a, is now a times r. But because I know I'm about to do a little bit of algebra math right here, I am instead going to line it up with its buddy right here. So a times r became ar for our first term. Our second term is now ar squared, ar cubed. We are going to get out to ar n minus 1, but this guy is going to get multiplied by r as well, and we're going to get as our final term ar to the n. Right? Now that I have a ton of terms, all but 2 terms have a matching partner, I am now going to do some subtraction. This is going to give me S sub n minus r S sub n on the left. On the right, everything cancels except for the very first and the very last term. So I'm going to get here a minus a r to the n. Remember, our goal was to find a simple closed form expression for S sub n. So that's what I'm trying to solve for right now. I've reduced myself from a situation where I had n terms to discuss to a situation where I have guaranteed only 4 terms to discuss, which is obviously a huge benefit to us here. So now I'm just doing a little bit of algebra. I'm going to get S sub n times 1 minus r equals a times 1 minus r to the n. And I just got to do one division step and we are good to go. All right. So this says to me the partial sum of any geometric series is right here. All right. But what we are interested in is not, I'm trying to say my words to her there. We are not interested in partial sums, really. Right? We wanted to compute a partial sum just so that we could take a limit as n goes to infinity. Right? So let's go ahead and see what happens here. So, a couple things I'm seeing. Our answer here is going to depend on what r is, right? What I'm seeing here is our power on r is going to get infinitely large. So I'm noticing things like if r were 2, then eventually we'd be doing 2 to the infinity power, and we'd be doing some form of diverging off to infinity, right? On the other hand, I'm noticing that if r is something like zero point 0.5, then 1 minus zero point 0.5 to the infinity power, zero point 0.5 to the infinity power is going to be 0. And so it looks like we are converging there. So what I'm seeing here is that it looks like this limit is only going to converge if r is smaller than 1, or smaller than 1 in absolute value. If we have an r value that's bigger than 1 in absolute value, even like 1.01, then it will grow as n goes off to infinity and therefore diverge off to infinity. If we see any r values that are less than 1, then it seems like this guy will be getting infinitely small down to 0 as n goes to infinity and therefore converging in value. Right? And so, let me see, okay, yeah, I guess I'm just making my statements right here. Let's say here, if the absolute value of r is greater than 1, then we get that the limit as n goes to infinity of a times 1 minus r to the n over 1 minus r is going to be equal to, or I'm going to say is going to tend towards some version of a times 1 minus, some infinitely large value over something right there. And that's going to diverge off to infinity right there. On the other hand, and I'm obviously doing some, bad math notation here, but for the purpose of our investigation here, just our idea notation. Then in this case, if r is less than 1, if the absolute value of r is less than 1, then as n goes off to infinity, r to the n will go to 0. And so it looks like we're just going to get a times 1, which is just a. So what it seems like we can conclude is this. Geometric series will converge if their common ratio in absolute value is smaller than 1. What will it converge to? A divided by 1 minus r for an infinite number of terms. On the other hand, if what you multiply by to get your next term in the sequence is a number that is larger than 1 in absolute value, then that means that our terms are going to grow in size over the time of the series, and we are going to diverge off to positive or negative infinity right there. I just said the positive one. And so this is sort of our conclusion that we end up wanting to make right there. That we can see that sometimes our geometric series converge, sometimes they diverge. It depends on what this common ratio value is going to be. Right? And it also looks like what we converge to has a in it. So it also depends on us knowing what is the initial value that that sequence started at right here. So it seems like we can conclude that this sum, if we can write a sum in this form, then it is geometric, and it is convergent if, let's see here, we are convergent if absolute value of r is less than 1 to a over 1 minus r, and is divergent if the absolute value of r is greater than 1 to plus or minus infinity out there, right? We're going to diverge in some direction. So let's go ahead and take a look at some of the examples that we want to see that are associated with this guy. The first one is always, let's go ahead and do some stuff that we've already seen before, right? So this is the thing we've already done. We already decided that we think that this is equal to 1. I want us to see that this can be written as a geometric series, and therefore we can use our geometric series rules to conclude its value. So notice that the very important thing about a geometric series is that it always has a number to a power of n minus 1. Your algebra beating stick job this week is to force things to look like you want them to look inside of our sums like this. So I think that I can rewrite this guy as the sum of, first I think I can do this, right? Because 1 to the n is always just 1, so I think that's equivalent. Now what I'm seeing is this is almost like what I want, except I don't want that to be to the power of n. I want it to be to the power of n minus 1. I want one fewer multiple of 1/2 included in this part of the sum as we currently have. So I'm going to write this as 1/2 times 1/2 to the n minus 1. All right. So those two little algebra steps right there have now brought me into a format where I look like the sum of a times r to the n minus 1. That was my really important thing I needed to do. So what I can now see is that since r equals 1/2 satisfies absolute value of r is less than 1, this series converges. To a over 1 minus r. In our case, a is the leading coefficient. That's the 1/2 I have sitting right there. 1 minus r is the base of the exponential, and that's 1/2. This is now 1/2 over 1/2, and that's 1. So it looks like we got the exact same result that we were expecting to see right there, but using our ideas about geometric series rather than having to use some geometry or coin flipping game like I made up right there, which are less reliable ways to go ahead and get our convergence value. So remember, geometric series don't always converge. You need to know when they converge. They converge when the base of the exponential is within 1 of 0, right? Absolute value is less than 1. Since this had an absolute value of its exponential base being less than 1, I knew it converged, and I knew what it converged to, a over 1 minus r. So recognize we kind of had to rewrite it in this format to know what our a and what our r were, so that we knew that it converged and so that we could compute its value of convergence right there. So let's look at two more examples and we'll call it a day here. Find the sum of this given series right here. So the important thing that's happening here is I'm not giving you any sort of summation notation. We need this written in the sum of a times r to the n minus 1 form, or else we just don't know what to do right now, right? So what I want to do is I want to figure out what is r, and I'm always going to do that by looking at the common ratio. What did I multiply the first term by to get to the second term? I can literally just say 3 times, well, that's just what I should write right here. 3 times r is 2. That says my common ratio is 2/3, right? Or I could say 2 times r is 4/3. And I divide both sides by 2, and that tells me r is 2/3. Or I could say 4/3 times r is 8/9, and I multiply both sides by 3, and I divide both sides by 4, and I get the r is 2/3 right here. So see, I confirmed that it's a geometric series by seeing that there is exactly a common ratio of 2/3 between all of the terms, and it also looks to me like we started at the number 3, and so therefore and a equals 3. That's always our initial value right there. And so it seems like this series, 3 plus 2 plus 4 thirds plus 8 ninths, an infinite series, is equal to the sum from n equals 1 to infinity of 3 times 2 thirds to the n minus 1. Man, you really need to stop and double check yourself before you move on from making huge claims like the one I just made right here. It is very easy to be off by a little bit when you write these things. You really need to stop and like plug in a number here. When I plug in n equals 1 as my very first value, 1 minus 1 is 0. 2 thirds to the 0 is 1, and we get a total of just 3. That does agree with my very first term here. So I know that 3 is what we get first. If I am looking at plugging in n equals 2, 2 minus 1 is 1. And so that would be giving me my second term. 2 minus 1 is 1. So I am going to keep one copy of 2 thirds. 3 times 2 thirds is 2. And what do you know? 2 is the second term in our series right there. So really like take your 60 seconds and double check when you kind of boldly make a statement. Oh, I discovered that this sum is actually equal to this summation representation. It's really easy to be off by 1 or something like that in these cases. So stop and compute a few terms for yourself and verify that you're correct. Right? So here we can see a equals 3, r equals 2 thirds. And so I think that I can now say, since r equals 2 thirds satisfies absolute value of r is less than 1, this geometric series converges to a over 1 minus r. A is 3 over 1 minus 2 thirds. That's 3 over 1 third, and that is 9. So here we have determined the sum of an infinite series by just doing one little quick operation, because we've discovered a way that we can, instead of adding up n terms, we can just look at just a couple of terms to help us kind of decide where we're headed with this stuff, right? So anytime that you see a series, I kind of, and it says, what does this converge to? I am always hopeful. I'm like, man, I hope this is geometric, or else I'm going to have to do a whole bunch of work. If it's geometric, I just got to get out my algebra beaten stick, force it into this summation form representation, decide what a and r are, just very quickly confirm that r is within 1 of 0, and then compute a over 1 minus r. And that's all we got to do. Before I walk away from this one and do one last example, I do want to say to you guys, like, this general formula that we came up right here, still super practical for computing partial sums. We are just always talking about infinite sums, like currently in the context of this class, but like this formula is a standalone formula, also super practical for just saying add up the first n terms of any geometric series. This one doesn't have to converge or diverge, because even if we're looking at this infinite series that would diverge, the first 1,000 terms are going to converge because we're only adding up 1,000 numbers, right? So this standalone formula is very practical for computing partial sums, which is a practical thing to be able to do. It's just that in this class, we're focusing mostly on our infinite series and sequences here. And so in our purposes for right now, the reason we computed this guy was just to take its limit, which sort of reduced it down to this case right here. But again, this is a standalone formula, is practical. We're just not going to use this extensively for our purposes in this chapter of this class. So let's look at one last little example here, just something that has a little less numbers in it, a little more variable in it, just so that we can make some broad cases here. This is a really good question because this is setting us up for a lot of the statements that we're going to be making in a few sections, right? So this is sort of a look ahead question right here. This is me saying, listen, I think that this series probably converges, but not for all values of x. Depending on what I let x be, this might converge or diverge. So what I want to know is what values are possible for x if I want this thing to converge, and if I did pick one of those values for x, what would this converge to? All right. So this is, again, the really important thing I think for you to see here is that there's really two variables of interest. There is x, which is a parameter in this case that we are allowed to vary. There is n, which is a little bit more, in a sense, our true variable, because that is the summation variable. It's the thing that we couldn't extract past that sum symbol right there. So what I'm seeing is we could rewrite this guy as the sum of x over 3 to the n, right? So this looks sort of like a geometric series formation, but I want that to be n minus 1. So that I can write this now as x over 3 times x over 3 to the n minus 1. I'm picking off one term just to let it represent a. So we have a equals x over 3, and r also equals x over 3 in this case right there. It looks like they match. We've got a, we've got r. Okay. But I'm not sure if this is always going to converge, right? If x is just like 40, then we're just multiplying by 40 thirds every unit of time. From a number that was bigger than 1, we're clearly going to diverge, right? So to converge, we need to have that our common ratio is less than 1. We have that our common ratio is x over 3, so that's what I need to be less than 1. So I can just do a little bit of algebra right here and just write this as negative 1 is less than x over 3 is less than 1. And since I'm not going to multiply by any negatives here, I'm just going to multiply both sides, or all three sides by 3, and say negative 3 is less than x is less than 3. So this is concluding to me, if we choose any x value between negative 3 and 3, this series will converge. For all other x values, this series will diverge. Our very last question of the day. What does it converge to? If it is going to converge, what does it converge to? So I'm not saying, I'm assuming that x is between negative 3 and 3. Those are the only scenarios in which we will experience convergence. What will it converge to? Well, it'll converge to a over 1 minus r. In our case, that's going to be x over 3. That was our first term, over 1 minus, and x over 3 also happened to be our common ratio. So I'll just do a little bit of algebra here. And it looks like any time that we choose some x value here, we automatically have a sum associated with that infinite series. So this is really cool now. Now we've determined what is we are going to come to define this idea to be a radius of convergence. We say that this one parameter series with a parameter of x will converge in a radius of 3 about x equals 0. That is the convergence radius for the parameter x. What will it converge to? If x is between negative 3 and positive 3, then the sum of the series is x over 3 minus x right there. We have a general form for the value of this series of this sum, regardless of what. And again, notice there's an infinite number of numbers we could plug in for x and this will converge. We know what all of their convergent values are, x over 3 minus x, just by doing a little bit of algebra right there. So I do really like these questions as well, especially because they're kind of leading us towards where we're going to be going with talking about parameterized series and saying, under what circumstance will this series converge? What values of these parameters cause convergence and divergence? We're starting to poke our way into those questions with this little example right here. So I really think these the geometric series are really probably the easiest part of this section. It's kind of why I saved them to the last, because I know that the proofs can kind of get overbearing there. But the geometric series stuff is pretty nice. It really boils down to a lot of your intuition about exponential functions is what you need to know about for geometric series. Just recognize that this looks like ab to the t. The variable is up in the power. N is our variable when we are within a sum over the first n terms. And so Think exponential stuff when you think geometric series. That's exactly what we're kind of constructing here, is an exponential function that describes each of these numbers, is in essence what's really happening right there. So that wraps it up for me for 11.2. And I am going to see you guys for 11.3 tomorrow, when we are going to bring this back to the calculus that we recognize. What we're going to ask tomorrow now is, how do sequences and series help us with integration and vice versa? How are these guys going to be related to each other? Maybe we can skip out on performing some integrals if we can rewrite them as sums. Maybe we can skip out on computing some sums if we rewrite them as integrals, or at least get some ideas of boundedness from one another, which again, we now know boundedness is directly related to convergence by the bounded monotonic theorem from 11.1. And maybe as my last statement for the day, as I always say 16 times as I'm wrapping up anything here, remember, for that bounded monotonic theorem that we got, that only applies to sequences. And that's why it's very valuable for us to recognize that the convergence of a series is exactly the same thing as the convergence of the sequence of partial sums. Rewriting a series as its equivalent sequence of partial sums now gives us access to things like the monotonic bounded theorem can prove that this sequence converges, which would therefore be allowing us to say that this series converges that we might be working with, right? So recognize that our tools only apply in one certain case, but if we can just kind of jump around to alternate representations that satisfy those cases, then knowing that theorem in one context still gets us to where we want to be in other contexts that are out there. Okay, that's actually it for me now today. I will see you guys for 11.3. Thanks for you guys being in chat, and I will see you guys next video.